So maybe I will just start with my little introduction. Uh, about me, my name is Magdalena Nowak. I am 20 years old student from Poland. I'm studying at the Military University of Technology in Warsaw. Now I am on my winter break at my home. Uh, yeah, and exactly, I am passionate about space technologies, about space engineering, satellites, radio telescopes, about satellite communication. Yeah, and I'm studying space and satellite engineering. So exactly, this is the major which describe me from head to toe, I can say. Apart from that, I'm a total music lover, total music freak. Especially, I love rock music. I love new metal, everything from the early 2000s and some of 19 and also 18 music. And I'm a CD collector. I also have some Bauhaus tapes. So I can say that I'm kind of old technology lover at some point. Uh, okay, I think that's all about me. Of course, you can see that there is a contact. For me, you can see my Instagram, you can see my LinkedIn and my Gmail account. You can write me anytime. I check my email box and my direct messages a few times during the day, so I'm pretty sure that I won't miss your message. Uh, okay, so hello and welcome to my presentation about satellites and radio telescopes technology. And here we have our lecture outline. I believe that satellites and radio telescopes are quite essential tools in modern astronomy. Uh, Satellites orbit the Earth to gather data from space, while radio telescopes on the ground capture radio waves from distant celestial objects, and working together, they provide a more complete view of the universe. So, exactly by offering valuable insights into galaxies, black holes, and other cosmic phenomena. And this cooperation helps scientists explore space in ways that were not possible before. So I believe that it is such a cool object, such a cool topic, and it's a pleasure to share with you with my point. Okay, so let's go through the learning objectives, sorry, for today's lecture. I believe that they will guide our exploration and ensure that we cover both the current state and the future directions of space technology. Uh, also, I have a little idea I will share with you. Mm, as this session should be more interactive than passive, so it can be just my lecture, but it should also include your ideas. Mm, I prepared three exercises. At the end of each part, we will have three parts: one about radio telescopes, one about satellites, and one about cooperation between those two tools. And also, I was thinking about something like making notes. You will have this presentation. You will have my speech. Uh, my idea was something like that. You are making notes about all things you will consider as interesting. And at the end of the lecture, you will send me your notes. And maybe uh, after all of you send me your ideas, your notes exactly, we will make a kind of brochure, a kind of small handbook about radio telescopes and satellites and how they can cooperate, something like that. If you are interested, you can do such a thing and send me at the end of this lecture. And also, we will have these three exercises. I will send you a link to the whiteboard on which you write your ideas. I hope that it will work, but if not, I just prepare a quick Google Docs document, and you will have some space to write your ideas. Okay, let's go back to our learning objectives. First of all, we will describe how satellites and radio telescopes function, and our goal is to understand the basic principles behind these technologies, and we'll look at how satellites are used for communication, for Earth observation, and navigation also, as well as how radio telescopes contribute to space exploration and astronomical research. Next, we will explain the key engineering and design challenges involved in these technologies. We will discuss various technological and engineering uh, hazards, hurdles that must be overcome when designing and building satellites and radio telescopes, exactly. And this also includes considerations such as material selection, energy sources, and also dealing with environmental conditions. And following that, we will identify the social impact of satellites and radio telescopes, because we'll explore how these technologies are applied in real scenarios, in real world, such as even GPS navigation and weather forecasting and global communications, and examine their overall influence on society and scientific progress. And finally, we will discuss future trends and challenges in space technology. We'll dive into potential advantages and maybe advancements in satellite and radio telescope technology, exactly focusing on current trends, on emerging trends, and possible innovations, and also the challenges that engineers and scientists may face in the years ahead, exactly. Okay, so now we will have the part one, so introduction to radio astronomy. And okay, let's start with that part. All right. So first of all, some of history. The beginnings of astronomical observations, as we know, date back many centuries, many centuries. But then only those made with the naked eye. And over time also with the use of professional optical instruments, such as telescopes. And this trend continued for centuries. And overall, during the last century, there was a certain turn I must say. One could even say a breakthrough. This is when the first printed mentions of radio astronomy appeared. In the 1930s, if I remember it well. Yeah, I'm right. The Bell Telephone Laboratories employee, Karl Jansky, noticed a certain regularity in the time of the day and the alignment of distant stars in which interference occurred on a large antenna. And he was also the first to state that they may be even of extraterrestrial origin. So he was therefore receiving radio waves from the center of the galaxy, quoting Kurt Supplee. Today we know that he initially conducted observations of wavelengths of approximately 15 meters, and this was in a range of which observations of, for example, Jupiter, are currently carried out. And nearly 30 years later, a pair of researchers from the Bell Laboratories, so R. Wilson and A. Penzias, oh my god, kinda difficult surname. They tried to get rid of the source of the static background from their radio telescope, but they failed. And also, after consulting with astrophysicists, they concluded that it must be relic radiation, actually. Do I have here? Yeah, exactly. Okay, and its presence was confirmed after 30 years by a NASA satellite, the Cosmic Background Explorer, COBE in short. What interested them most, however, was how the same microwave frequency and wave intensity did not change, neither with the time of the day or night, nor with the season. And the indications of the possible origin of the signal from space were clarified as coming from outside our galaxy. The above-mentioned COBE satellite helped to finally solve this puzzle related to the Big Bang Theory. And this was a summary of the history of radio astronomy. Okay, now the best part. So the components of a radio telescope. Yeah, each radio telescope consists of three main parts, regardless of whether we are talking about 27 antennas of the powerful, very large array radio telescope in New Mexico, for example, or the already mentioned Arecibo and LOFAR. Here are the parts. We have antennas, or antenna, assemblies for collecting radio waves. Most radio telescopes have parabolic mirrors, as you can see on this photo. They do this in the same way that a curved mirror can focus visible light to a point called the focus. An antenna is placed at the focus of the radio telescope, where all the energy of the collected radio waves is concentrated, and weak radio signal amplifier system. We have also something like that. It is worth emphasizing that the radio wave in the antenna creates a very weak current. It is this signal that is sent for analysis. And nowadays, amplifiers are extremely sensitive, and they are usually cooled to very low temperatures to minimize interference caused by noise generated by the movement of atoms in the metal. And we also have a signal recorder, as you can see on the slide. Okay. And what we can do with these radio telescopes? Actually, they allow us to observe the universe in a way that goes beyond just visible light. While optical telescopes gather visible light and infrared radiation, radio telescopes detect exactly radio waves. I believe it is not a mystery anymore. And it is a crucial part of the electromagnetic spectrum. And celestial objects such as stars, pulsars, quasars, and black holes, and even entire galaxies emit powerful radio waves. And these waves carry valuable information that helps us understand the nature of these distant objects. And just like optical telescopes focus visible light for analysis, radio telescopes gather weak radio waves from space, amplify them, and convert them into the data that can be studied. Exactly. This capability opens up a whole new dimension of observation, and by interpreting these signals, scientists can learn more about the universe, including phenomena that are visible to the human eye or optical instruments. So we can look with this second eye at objectives which are visible for us or which are not visible. So I believe it's a win-win situation for us. Now more about these radio waves. So they cover a wide range of wavelengths from a few millimeters to several meters, which is much longer than the wavelengths of visible light that optical telescopes detect. For example, visible light has wavelengths that are just a few hundred nanometers in length. And this difference in wavelength is significant because it allows radio telescopes to see parts of the universe that are completely hidden from optical telescopes. And exactly, ground-based radio telescopes are most effective at detecting radio waves in meter, centimeter, and millimeter range. These wavelengths can penetrate Earth's atmosphere without being reflected or absorbed, and longer the radio waves, however, get reflected by the Earth's ionosphere, while shorter waves are absorbed by molecules like oxygen and water vapor in the atmosphere. And one of the great advantages of radio astronomy is that it is less affected by atmospheric conditions than optical astronomy. Radio telescopes can operate effectively day or night, and they aren't hindered by cloud cover or other weather conditions. For the shortest radio wavelengths, which are close to the far infrared spectrum, high-altitude observatories are often used to minimize atmospheric interference. Okay. Exactly, radio telescopes play a critical role in astronomical research, often working in collaboration rather than isolation. One powerful technique is to arrange them into large arrays, like the Very Large Array in New Mexico or LOFA here in Europe. These arrays combine signals from multiple telescopes, which significantly increases the resolution of the images we can capture. allowing us to observe fine details in distant cosmic objects. And another advanced technique used in radio astronomy is interferometry, where radio telescopes spread across different locations are synchronized to act like one giant telescope, like one giant antenna. This approach, known as very long baseline interferometry, so VLBI in short, can create a virtual telescope with an effective size as large as the distance between the individual telescopes. So an example of this is the Event Horizon Telescope, which was crucial in capturing the first ever image of a black hole by linking radio telescopes around the globe. These techniques enable us to push the boundaries of what we can observe in the universe. And yeah, exactly. Here you can see the photo of LOFAR, of the few radio telescopes which are in the LOFAR network. And this is exactly in Poland, so where I live. I haven't seen it yet, but I hope that I will be able to see them soon. Yeah, okay. Mm, and here is one of the antennas of the Deep Space Network, but about it later. I won't talk about it yet. Okay, and now we have the exercise. Here you can see the I forgot that part. Sorry about that. Okay, I want you to imagine that it is a year 2045 and think about what new discoveries radio telescopes might help us make and who or what we could communicate with. So, distant stars, space probes, or even other civilizations. Yeah, and you can write your ideas on the whiteboard. I will send you a link to the Figma board. We will see if it will be working. As I said, if not, I will just create a new Google Doc and we will work there. Okay. I believe you can see the link on the chat. And now I move to my whiteboard. Okay, if maybe someone will let me know if the whiteboard is working, if everything is okay, I will be grateful. Okay, I saw that. Super. I'm not sure how much time you will need. I see that I've already wasted about half of the time I have for my lecture, so maybe around 5 or 10 minutes. Maybe you will be that fast, or maybe I will be just faster during the other 3 parts. Okay. So let's just say I will come back after 5 minutes. I will drink some water because I feel all of these words in my throat now. Okay, and I'm waiting for your ideas. So we will see each other in 5 minutes, okay? All right, I believe welcome back after 5 minutes. I'm looking at your whiteboard and I must say you have great ideas. Oh my God, I'm so proud of you. Okay, um, maybe just do something like that. I will end my lecture very quick, and if we will have enough time left after it, we will come back to your ideas. But I must say once again, they are very great. Yeah. Okay. So uh, let me just open it again. Okay. And now we are moving to the second part. So exactly introduction to the satellites. Okay, so let's start with the basics. Uh, okay, so the word satellite originates from the Latin satellis. I believe that I'm spelling it well, meaning companion or servant. So, in modern terms, an artificial satellite refers to any man made object that orbits a planet, typically Earth. And there are two main types of satellites. So, we have natural and artificial satellites. Natural satellites are moons. So, like our own moon, while artificial satellites are electronic devices created and sent into space by humans. These artificial satellites include meteorological, navigational, and telecommunication satellites, and additionally, space telescopes, such as the Hubble Space Telescope and Cassini, which orbit other planets or even the Sun, fall under this category. Yeah, and now, okay, orbits. So now let's talk about how these artificial satellites operate. Uh, to place a satellite in orbit, it must be launched into space using rockets with precise calculations of speed and angle to maintain its desired orbit. And exactly, artificial satellites are placed in different types of orbits depending on their function. And we have, for example, low Earth orbit, so LEO, which ranges from 160 to 2000 kilometers above the Earth, and medium Earth orbit from 2000 to oh, 35,786 kilometers. Sorry, but numbers were never my strong side of the English language. Now we have high Earth orbit, which is anything above 35,786 kilometers. And we have also other specific types of orbits. For example, this one called geostationary orbit, which is very crucial for telecommunications. And satellites in this orbit are exactly 35,786 kilometers above the equator and rotate with the Earth, staying fixed over the same location. Yeah. And exactly, telecommunication satellites are primarily composed of two main components. So we have the spacecraft bus, also known as the platform, and the communication subsystem. And the spacecraft bus handles essential tasks like maintaining the satellite's orbital position, ensuring stability in space, and directing antennas toward target regions on Earth. It also provides protection from extreme temperatures and supplies power to all of the satellite systems. And the communication subsystem, on the other hand, manages the reception, amplification, and transition of radio signals. So now, in my research group, for example, I'm exactly working on the communication subsystem on our CubeSat model. Uh, okay. The mechanical structure of the satellite, mm, it varies because older designs used a cylindrical structure, as you can see on this photo of a satellite with such a structure, which relied on spin stabilization. Antennas would remain fixed while the rest of the satellite spun. Modern satellites, however, use a box-shaped structure stabilized by gyroscopes for better control. In addition, the spacecraft bus includes telemetry, maintenance, and propulsion systems. So telemetry gathers data from the satellite status and sends it back to ground stations, and maintains systems. Uh, they receive commands from Earth. And lastly, propulsion systems include engines and fuel tanks for adjusting the satellite's orbit and correcting antenna position. Okay. Now the energy system. This system is very, very crucial. And we can have, for example, solar panels or photovoltaic cells. They are the primary energy source. And during periods when the sun is blocked, let's say the sun is blocked, the satellite relies on, for example, nickel hydrogen batteries and also thermal control. It is another very important aspect because satellites need to manage the heat produced by internal equipment while also being protected from the very extreme temperatures of space, which can range from very high to as low as minus 270 Celsius degrees. And heat dissipation systems and thermal shields help ensure the satellite's components remain with operational temperature ranges. Okay, now we have satellites repeaters, which are a critical part of the communication system. And there are two main types of repeaters. We have a transparent, also known as non-regenerative, and regenerative or active repeaters. And transparent repeaters are simpler, let's say. They are simpler because they receive signals, shift their frequency, and retransmit them back to Earth. And they are widely used in both digital and analog transmissions, such as satellite TV, for example. And regenerative repeaters, on the other hand, are more advanced and used exclusively in digital transmissions. They can not only retransmit signals, but also regenerate, concentrate, and even switch them. If the satellite is part of network with inter-satellite links, these repeaters can also participate in routing data between all of the satellites. Okay. Telecommunication satellites use a variety of antenna systems, each designed to cover different areas on Earth. Global beam antennas are simpler and can cover up to 45% of the Earth's surface, and hemispherical beams antennas cover around 20% of the Earth. Yeah, 20. Uh, while sound beams antennas focus on smaller areas, covering about 10%. And finally, spot beams antennas are highly precise, covering very small areas with a narrow beam angle, typically even less than 1 degree, often using parabolic reflectors. Okay, and now we will have, yeah, frequency. Yeah, let's look at an example of how frequency plans are allocated for communication satellites. So, in the Q band, which is commonly used for geostationary satellites, they are typically a 500 megahertz bandwidth allocated for uplink, where signals are sent from Earth to the satellite, and similarly, sorry, another 500 megahertz bandwidth is allocated for downlink, where the satellite sends signals back to Earth. And this setup ensures efficient and reliable communication between satellite and ground station. Okay, and yeah, here are the photos of both cylindrical and box satellites. Okay, and now yeah, finally, let's discuss some challenges related to artificial satellites. With the growing number of satellites launched into space, the, mm, there, there's now a significant amount of space debris orbiting the Earth, and many satellites are no longer active, creating crowded and potentially dangerous, even dangerous situations for operational satellites. And currently, there's no comprehensive space law that regulates the number of satellites launched, leading to congestion in Earth's orbit. And despite these challenges, technology has made it easier to observe and track satellites. Tools like, for example, Heavens Above app can predict when satellites, including the International Space Station, for example, will be visible from Earth, allowing us to see them with the naked eye. Okay, and yeah, we have the exercise too. So now I want you to design an instrument. It can be a small instrument for a satellite and decide what it would measure. So, for example, I don't know, electromagnetic waves, cosmic phenomena which you want to observe. You can write or draw it on the whiteboard. And again, we will see each other after 5 minutes. And I will continue with the lecture. And at the end of the lecture, we will switch to your ideas and maybe discuss them. Okay. Link is the same. You will have the same whiteboard. And yeah, exactly. We will see each other in 5 minutes again. All right, okay, 7 minutes. And I can see that you are working again and you have another great ideas. Okay, um, I will just do quickly the first part and then we will switch to our discussion. Okay. Mm, all right, so now the final part. Exactly, the third part, so the cooperation between satellites and radio telescopes. And an example of the cooperation between satellites and radio telescopes is the ESA, so European Space Agency mission called Genesis. And ESA has approved funding for the Genesis mission, which aims to revolutionize satellite geodesy by integrating multiple tracking techniques for um, unprecedented precision. This will add first mission. This will be a first mission to utilize not only traditional satellite tracking methods, such as GPS and Galileo signals, but also radio telescopes, laser ranging, and Doris ground stations. And this mission will allow for more accurate geodetic sorry, measurements, targeting a precision level of even 1 millimeter, essential for monitoring Earth's changes, such like sea level rise, and which are driven by climate change. Okay. Yeah, the Genesis mission will be the first to combine satellite tracking via radio telescopes with other techniques. So the radio telescopes, which typically observe distant cosmic objects like quasars, will now track the Genesis satellite, marking a significant technological breakthrough, I will say. And this collaboration will overcome the challenges of tracking fast-moving satellites and enabling precise positioning and timing measurements. And by integrating 4 different tracking methods, so radio telescope, Doris, satellite laser ranging, so SLR, and GNSS signals from GPS and Galileo, Genesis will set a new standard in satellite geodesy. Not sure if we will have a schematic. Yeah, we will have a schematic arrangement of selected components of the Genesis mission, which will launch next year, so 2026. I hope to see that launched very soon. Okay, and now I believe the best part. This is my favorite project personally, and I hope that you will also like it. So the Deep Space Network, or DSN in short, it is NASA's largest and most advanced telecommunication system, and it is managed by the Jet Propulsion Laboratory. And yeah, exactly, the DSN is essential for supporting interplanetary spacecraft missions. What makes this network unique is that it also plays a role in radar and radio astronomy, helping us gain a deeper understanding of the solar system and the larger universe. So the DSN operates through 3 main sites strategically located around the world. So we have one in California, another near Madrid in Spain, and the third one near Canberra in Australia. And this global positioning allows for continuous communication with spacecraft as Earth rotates. Okay. Mhm. Yeah, DSN isn't just about maintaining communication with spacecraft. It's crucial for their operation. And the network allows us to command spacecraft, track their progress, and monitor their health even. Additionally, DSN supports science investigations that go beyond data collection. For example, it helps probe asteroids and analyze the interiors of planets and moons. Each of the three DSN sites houses several large antennas, including powerful 70-meter parabolic dishes. These antennas are designed to detect extremely faint radio signals from spacecraft that are billions of miles away. Mm-mm. Yeah, one of the standout features of the DSM is a massive 70-meter antennas located at each of the three sites. And they are the largest and most sensitive in the network. Their size and sensitivity allow them to track spacecraft that are incredibly far away from Earth, making it possible to transmit and receive data from vast distances. And the work done by these antennas is vital for the success of space missions, enabling us to gather crucial scientific data and explore regions um, that are in the universe and which were even unreachable yet. Uh, Not sure if I have this screenshot. Yes, I have the screenshot. In the screenshot, you can see a view of the NASA web program. Uh, I provided the address under my under my slide, but unfortunately, I'm not sure if it is working now. But the last time I checked that program, it was turned off. I don't know why. It's such a shame because it is a great program on which uh, we could see the current status of the DSN suit antennas and spacecraft and other instruments with which they contacted, as well as a map with the location of equipment and antennas on our globe. Uh, yeah, exactly. Very good program. Not sure if it's working now. Uh, I hope they will turn it on soon again. Uh, okay, and now we have the summary. So, exactly, the collaboration between satellite technology and radio telescopes has revolutionized many aspects of our daily lives. For instance, GPS is a direct result of satellite technology, of course, providing us with precise navigation and timing that powers everything from smartphones to critical infrastructure. Satellites also play a key role in monitoring our climate, giving us the ability to track weather patterns, sea levels, and even predict natural disasters. Uh, yeah. Now we will have the third exercise. Mm, my idea was to draw a kind of collaboration map, mm, showing who observes what, how data is exchanged, and how what results could come from their cooperation. Mm, Maybe let's say that you will just tell me your ideas. You don't have to write them down on the whiteboard. Mm, I believe that I finished my presentation. Yeah, exactly. Here are the sources. Here is the Thanks for your attention. I just move to your ideas on the whiteboard, and I don't know, maybe you want to tell me about your ideas, maybe why you wanted to design such a satellite instrument or something like that. Now we will have a few time for Q&A if you want, of course. You can say some things and we can talk about them if you want. So now I just listen what you have to say.
Thank you so much for your time, Magdalena. It truly was such a wonderful session. I, for one, didn't know that there's so much science that goes into space studies. I've always focused more on the biology aspect. So your passion for space and your passion for STEM truly speaks when you give us your sessions. If you guys do not have any questions, we can conclude the session. Everyone give her a massive applause. Oh, we can already see that happening. And thank her for her amazing session. She took time from her very busy uni schedule to come here and do this presentation for us. So thank you so much for your time once again.
Thank you once again for having me. It was such a pleasure.